Good morning. We're on to Unit 7 where we're going to talk about polynomial and sinusoidal functions. This is your very last unit. Hooray, you did it. Almost. Okay, so we're on to Lesson 1 notes. I'll go through a few of the examples here. Okay, so first we're going to talk about polynomial functions for the first couple lessons, and then we'll get into sinusoidal ones at a later time. So first of all, what is a polynomial function? It's a function defined by any defining equation in this form. So this looks like a kind of complex way of writing it, but basically you have some number and x raised to some exponent, etc. And then there's some terminology here as well. So here's an example of a polynomial function. The 3 here is called the exponent. Remember, when you're writing polynomial functions, you always go from highest degree to lowest degree. So this one is already in that order, which is great. So when I look at this here, this -2 is called the leading coefficient. And then the very last number, if it doesn't have a variable with it, is called the constant. Okay, and for a polynomial function, you have to be able to identify if it is a polynomial function or not. Some things to keep in mind if you look right here. This one is not a polynomial function because it has a negative exponent. So if you ever have a negative exponent, or in other words, a variable in the denominator of a fraction, you don't consider it a polynomial function. Okay, the next one here, this is also not a polynomial function because there's a variable under a radical. So you can't have a weird variable under a radical, or in other words, you can't have a fractional exponent. Okay, and for the next one, this one is not a polynomial function because, again, you have a variable in the denominator. If I was to rewrite this one, you could write it this way and you'd see it has a negative exponent, which is not allowed. So I won't write that one out. Those are all not considered polynomial functions. So in the chart here, I'm not going to go through all of these. You can kind of see from my notes. You're supposed to identify if it's a polynomial function, yes or no. The only one I will touch on is this one here. Be careful with this one. It's not written from highest degree to lowest. So before I would answer all the questions, I would rewrite this one. This has the highest degree, so it should be -2x to the 5 plus 3x squared plus 4, and now you can answer the questions. All the variables are there, all their exponents are whole numbers. This is a polynomial function. Degree, if you look at the each individual term, this term has a degree of 5. It's whatever the exponent is. This has a degree of 2, and whatever is the highest exponent is your degree of the polynomial function. Leading coefficient is going to be -2, and my constant term is the 4. Then you can look at the rest of the examples there in a little bit. Okay, so we're going to get into graphing polynomial functions. So they all kind of follow patterns that you can see based on the equation. So first we're going to look at the end behavior. So you can use the degree of a polynomial function and the sign of the leading coefficient to determine the end behavior of the graph of the polynomial function. So first we're going to look at even degree polynomials. Anything with an even degree. So that means if I find the degree of polynomial function and the degree is either 2, 4, 6, 8, etc., it's an even degree, then you know they're going to follow these patterns. So we're going to study these graphs here and see if we can figure out a pattern here. What you'll notice with even degree polynomials is that both the starting part of the graph and the end part of the graph, either both are going to be pointing up or both are going to be pointing down, no matter what. If you notice this one, the start is pointing up, the end is pointing up. This one, the start is pointing down, the end is pointing down. So they're either both up, both down, no matter what, if it's an even degree polynomial. Then you'll notice we can determine if they're both pointing up or both pointing down. If you look at the leading coefficient, Here, your leading coefficient is positive. Here, my leading coefficient is negative. If you have a positive leading coefficient with an even degree polynomial function, both your start and end arms will be pointing up. If you have an even degree polynomial function and a negative leading coefficient, that first number in the very front is negative, then both your arms are going to be pointing down. So I'm going to summarize that in the chart here. And again, you're going to have to remember where your quadrants are when you do this. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So again, we look at the degree of the function. If it's even and it's a positive leading coefficient, that means that both your start and end of your graph are going to be pointing up. There might be a bunch of stuff in between, but you know that it's pointing up for your start and at your end. And then if it's a negative, then you know that it's going to start and end pointing down. So the language that we use for end behavior is that I know it's going to start in quadrant 1 and end in quadrant 2. Because if you look at the quadrants here, you know it's going to start going up, and there might be some stuff in between, and then it's going to end going up. So it starts in quadrant 1. Oh, that should say starts in quadrant 2, ends in quadrant 1. That's a typo in my notes, so let's fix that there. Starts in quadrant 2, ends in quadrant 1. My apologies. Okay, if it's negative, that means it's going down. So that means it's going to start in quadrant 3 and end in quadrant 4. I did that one right. Okay, so that is for even degree polynomial functions. Let's look if it's an odd degree function. So that's on the next page here. So looking at odd degree here, all different examples of odd degree functions. So if I figured out the degree of each of these, they'd be an odd number, like 1, 3, 5, 7, etc. And what you'll notice is it starts and ends opposite. Either one is up, the other one is down, or the other one's down, the other one's up. So it kind of looks like a kind of robot arms. And then you can notice this one here has a positive leading coefficient. This one here has a negative leading coefficient. So you can kind of see that if it's a positive leading coefficient, it's going to start pointing down and pointing up. And if it's a negative leading coefficient, it's going to start pointing up and end pointing down. So we can summarize that as well, and you can look and check out the other graphs. It's true for all of these. Even this one here, your leading coefficient is negative. So you can see it starts pointing up, ends pointing down whenever it has a negative leading coefficient and it's odd degree. So then we just need to summarize that in the chart below. So if it's positive, we know it's starting pointing down, ending pointing up. And if it's a negative leading coefficient, it's starting pointing up, ending pointing down. And if you use your quadrants, we're going to say starts in quadrant 3, ends in quadrant 1. Right? If you think about your quadrant, starts in quadrant 3, ends in quadrant 1. For negative, it starts in quadrant 2 and ends in quadrant 4. So if I look at that one, it starts in quadrant 2. So that means it's going to be starting this way, and it's ending in quadrant 4 if it has a negative leading coefficient. And all of these clues are going to help us graph all of these in a little bit. So a couple other things we're going to talk about. That's all end behaviors. So you can refer to your notes. Sometimes it's a little tricky to remember those or memorize them. Next, we're going to talk about zeros, roots, and x-intercepts of a graph. You've probably heard this language before. If I ever ask you to find the zeros of something, what it means is you're solving for the roots of the related equation. Basically, what you're doing is you're setting it equal to 0 and solving for x. So I show the work there. Instead of p of x, I'm going to put a 0. And And then I'm going to solve for x, and remember you can do this in several different ways. If you can do it by factoring, that's the quickest way. Otherwise, you can use your quadratic equation to find it. If I graph this, I'm going to get, or factor this, I'm going to get x minus 5x plus 1. And then you can solve it either the x minus 5 has to equal to 0, or the x plus 1 has to equal to 0. So I found the zeros, or x can equal 5 or negative 1. There's different words for this, they all mean the same thing. So if I ask you to solve this, if I ask you to find the zeros, if I ask you to find the roots, or ask you to find the x-intercepts, it all means the same thing. And what's handy about this is if you can factor your equation, then you know what the zeros are of the graph, which is the same as the x-intercepts in the graph. So if we use our graphing calculator, you can put this into your graphing calculator and then graph it. You'll see that your graph looks something like this. And you can see where your x-intercepts are. They're here and here. Your x-intercepts are where x equals negative 1 and 5, which is the exact same thing we found here. So you can see if you have a factored form of your equation, you can easily find the zeros of the graph, and then that's going to tell you where these points are here and help you actually graph it. And we'll put this all together in a little bit here, and I'll show you how it works together. Something new for you is section 3, multiplicity of a zero. So when we solve an equation of the form p of x equals 0, some of the roots or zeros may be duplicated. So let's say I had factored something, and when I factored it, it looks like this. That's a duplicate 0. I have x equals 1, but technically it happened twice, right? So that's called the multiplicity. So if it's happening more than once, you can determine the multiplicity, and then your graph does certain things during that time. So a root of the multiplicity of 1, so that's just our regular root that we find, is just going to pass straight through the x-axis. So when I'm drawing it, it's just going to come and shoot straight through, nothing fancy. If you have a multiplicity of 2, it's going to touch the x-axis but not cross it. So that means your line's going to come down, I say it gives it a gentle kiss here and then comes back up. That's if it's a multiplicity of 2. A multiplicity of 3 says it has a cubic shape of the x-axis. So in other words, if it's a multiplicity of 3, it comes up, and at the x-axis, it has a little zag, and then it comes up, delays at the x-axis just for a second before it keeps going. So that's going to come in handy. All those different things can help us determine what the graph is of the polynomial function. So let's kind of combine some of this knowledge together for the next page, and then we'll actually use it to start our graphing on the next page. So here we want to determine the zeros, state each zero's multiplicity, and then determine the degree of each polynomial. So most of the ones I give you will be factored already. So lucky for you, there's not a ton of factoring that you usually have to do. So the first thing we're going to notice here is we're going to determine the zeros first. So I'm going to do the first example here. So it's already factored. If I want to determine the zeros, it means I'm setting this equal to 0 instead and solving it. So that means either x plus 3 has to equal 0 or x minus 1 has to equal 0. And you can see your zeros are x is negative 3 or positive 1. Some of you might not have to do this step, and you can look right from here and see that x equals negative 3 and positive 1. That's great. You don't have to show your work for it. So I have two zeros, negative 3 and 1. Now I need to determine their multiplicity. Their multiplicity is how often that factor appears. So if I look at this example here, my exponent here is a 1 and a 1. I just don't write it if it's a 1. So that's technically your multiplicity, is your exponents on here. Okay, so I have a multiplicity of 1 for the negative 3, and I have a multiplicity of 1 for the positive 1. So now I found their multiplicities. It's just the exponent on your factor. And then it says determine the degree of each polynomial. Your degree is just your multiplicities added together. Because if you foil this original thing out, which you don't actually have to do, but if you actually FOIL and multiply it all out to put it in proper polynomial form, you'll see that your biggest degree is going to be an x squared. So you have a degree of 2. The quickest way you can do that is your degree is just your multiplicities added together. So my degree of this polynomial is 2. I'll just do one more example at the bottom here. Let's do this one here. So now we're going to look at this here. My zeros, I can see from here my x is -1 and my x is +2. If you need to write it out, you can. And now I can figure out my multiplicities. I'm going to look at the exponents. So this one here where I got the -1 from, my exponent is 2. So that's my multiplicity. And for this one here, where my x equals 2, it doesn't have an exponent. Technically it's 1. It is there. You just don't write it. So it has a multiplicity of 1. So now I found my zeros and my multiplicity. And you can even see how it relates to the graph. So my 0 is at -1 and at 2. Those are your x-intercepts. And then your multiplicity tells what your graph is doing at the time. So my -1 is a multiplicity of 2. That means when it comes up to this -1 portion, it's just going to give it a gentle kiss and then go back down. And then when it comes up to the 2, it's a multiplicity of 1, so that means it just shoots straight through without pausing at all. And then we want to figure out the degree. Your degree is just your multiplicities added together, which is a 2 plus 1. This is a degree 3 polynomial. Okay, so all that information culminates into how do we draw the graph of this. Yes, you can use your graphing calculator, but only to check after. So many people try to just kind of plunk it into your calculator, draw it, and get the wrong answer because the screen isn't showing everything that's going on. So I recommend don't use your calculator at all. Draw it, and then double check it with your calculator after if you like and see if it kind of makes sense. So let's do, I'm just going to do 3 of these examples. So we'll do the first one here. For graphing, you always need 3 things, and I wrote it at the top of the page there. In order to graph, you need to know the zeros and their multiplicity. That's your starting point. Multiplicity. You need to find your y-intercept. Makes your graph a little bit more accurate. We are just kind of doing a rough sketch, but the y-intercept will give you a bit more information about the graph. And then you have to analyze your end behavior. See where your graph starts and ends so you know how to start drawing it. Okay, so first of all, we're going to graph all of these with limited use. So in other words, don't use your graphing calculator, but check your answer at the end. So here's my polynomial here, and I want to say, is it an even or an odd degree polynomial? So here are my exponents, my multiplicities. When I add them together, I can see my degree is 2, which means it's an even degree polynomial. That means when I start and end, it's either both going to be pointing up or both pointing down. And then I'm going to look at my leading coefficient here, and I see that it's positive. Okay, so that tells me my end behavior. I'm going to skip down already to end behavior. I know it's even degree with a positive leading coefficient. That means that they're both going to be pointing up. Start and end pointing up. Okay, so that's a good piece to keep in mind. The next thing we're going to do is find the zeros and their multiplicities. So I'm going to look at my factored form here. Again, almost all of them are factored for you, so you don't have to worry about that. I can see my 0 for this one is x must equal 5, and my 0 for this one is x must equal -3. And their multiplicities are their exponents, and each exponent is 1. Okay, so from that, I can start drawing the graph a little bit. I have a 0 at 5, so that means I have an x-intercept at 5 and at -3. So I have both of those there. I'm going to start with that. Now I'm going to do the y-intercept. To find the y-intercept, remember you just put your x equal to 0 and solve. So I'm going to put my x equal to 0 in my original equation. And when I figure that out, I'm going to get a negative 7.5 as my y-intercept. So I'm going to draw that on the graph as well. 1, 2, 3, 4, 5, 6, 7.5. That's my y-intercept. Okay. So now I can actually draw the graph. I have 3 points. I can kind of see what's going to happen. It's going to start in quadrant 2. So it's going to start here. And then it's going to end in quadrant 1. So I know if it's starting here, it's going to come down to my x-intercept. Now I'm going to check my multiplicity. My multiplicity is 1. That means it shoots right through. Then it's going to loop back to my other x-intercept, which also has a multiplicity of 1, so it's going to shoot straight through. Make sure you put little arrows on your graphs to imply that those lines go on forever. Okay, so that is basically it. I'm just going to double check. End behavior, it starts in quadrant 2, which it does, ends in quadrant 1. They're both pointing up, so that's perfect. It goes through my zeros, my x-intercepts. The multiplicity makes sense. And here's my y-intercept. And it's nice to label that y-intercept as well. And that one's done. Okay, let's do another one. So now we're doing this one here. This is 2. This is a 1 here. We just don't usually write it. So when I add those together, I can see my degree equals 3. So it's an odd degree polynomial. And my leading coefficient here is negative. So that's the information I need to find my end behavior. So if it's odd degree with a negative leading coefficient, that means it starts pointing up, ends pointing down. In other words, it starts in quadrant 2 and ends in quadrant 4. Okay, now I'm going to keep going with my information. I want to find the zeros. So this one here has a 0 of 0, and this one here has a 0 of negative 1. Then I'm going to do their multiplicity. The one that I got the 0 from has a multiplicity of 2, and where I got the negative 1 from has a multiplicity of 1. I'm going to start to plot some of the points of my graph. So I have a 0 at 0. And at negative 1, so I know there's definitely that point on the graph. And now I'm going to do my y-intercept to figure out my other point. Set your x equal to 0 and then plug it in. When you do that in your calculator, you'll see it's at 0, which makes sense. My y-intercept is here, which I already had plotted anyway, so that makes sense, 0, 0. Now I have to draw it. Starting with my end behavior, this tells you whether we need to start here or here. I need to start in quadrant 2. So I'm going to start here, and I'm going to approach the negative 1, which has a multiplicity of 1. So that means I'm going to come down, shoot through it, but now I have to start bending up to get to the other 0, which has a multiplicity of 2. So that means when I come up to this one here, it's just going to give it a little kiss, and then it's going to go back down. Throw your arrows on there, and then just have a quick double check for everything. Zeros are good, multiplicities make sense. You know where it starts and ends, and that one is good. Okay, I'm going to try one more. I feel like I'm talking fast, so bear with me. At least you can rewind if I'm talking too fast. All right, so let's look at the bottom of the next page. I'll just do one more, and you can look through the other ones on your own. So first of all, we want to figure out what degree it is so I know where to start and end my graph. This has an exponent of 1. Don't forget that single x there still counts. So wherever there's a variable, it's going to count for your zeros and multiplicities. So when I add those all together, I get a degree of 6, which means I have an even degree polynomial. And I can see my leading coefficient is positive. So I'm going to skip down and do my end behavior right now. Even degree and positive means they're both pointing up. So it starts in Q2, ends in Q1. Okay, now I'm going to go and find my zeros. So from here, x equals 0. From here, it'll be a negative 1. And from here, it'll be a 2. Those are all my zeros. Whatever makes that expression equal to 0. So if you need to write it out separately for each one and solve it, do that if you need to. Otherwise, just look at it and see. Multiplicity is your exponent. So for this one where I got the 0 from, it's 1. The negative 1 is going to be a multiplicity of 3. And the 2, it's going to be a multiplicity of 2. I can start plotting those now. So I have a 0 here, at 0, at negative 1, and at 2. And then we're going to do our y-intercept. I can kind of guess where it's going to be already because I can see this point here is already crossing the y-axis, but let's show the work. So you're going to put in a 0 for all your x's. Put it in your calculator, you're going to see your y-intercept is at 0, which we already have. Now we can start actually drawing it using our multiplicity knowledge. Remember, if it's a multiplicity of 1, it shoots right through the x-axis. If it's a multiplicity of 3, it comes and it'll give it a little gentle touch. Oh, nope, I lied. That's multiplicity 2. If it's a multiplicity 3, it's going to come and do a little zag and then keep going. Okay, so it starts in quadrant 2. And when I'm approaching this negative 1, that has a multiplicity of 3. So that means I'm going to come down, do a little zag right here, and then keep going. Then for 0, it's a multiplicity of 1. That means I'm going to come and shoot right through. And then for 2, it's a multiplicity of 2, which means I'm going to come back down, give it a little kiss, and then keep going. Add your arrows, and that one is done. And again, you can pop that in your calculator and just see it should have that general shape, but you should be able to do it on your own as well. And don't hesitate to come see me at Google Meet or email me or at any time. I'm very happy to help or meet with you at Google Meet at any time if you have any questions at all. Have a great day.